20 August 1868, Central Plains Frontier, and a British manual table printed in 1888. In late 1860s reports from the Central Plains and Central Rockies, homestead cabins hit in Indian raids are repeatedly described as riddled with bullets. Thin plank doors and light wall logs were penetrated by rifle balls at 100 yards and more. County histories record doors shot to pieces, and walls full of holes after short engagements. 2 decades later, a British field engineering manual prints exact numbers for rifle-proof cover. 12 inches of fir logs or 6 inches of oak planking are listed as sufficient to stop contemporary rifle bullets at any range, while tests show about 5 inches of ordinary wood can be fully penetrated by musket fire at 100 meters. Homestead surveys from the American West describe rare, forted-up houses and cattle company buildings deliberately built from unusually heavy, straight logs with loopholes for defense, while neighboring cabins used lighter material. This episode treats a later frontier story of a settler mocked as foolishly picky in his log selection, whose walls allegedly stopped rifle fire during an 1860s raid, as an engineering test case, not a proven incident. Using raid accounts, blockhouse archaeology, timber data, and 19th to 20th century ballistics on wood penetration, we ask a narrow question. How thick, how dense, and how carefully selected did frontier logs have to be before a cabin wall became, in practical terms, bullet-resistant? Tend, January 1868, Central Plains and Central Rockies, U.S. frontier. A county history volume lies open to an 1860s raid. A homestead cabin left standing but badly perforated, with doors and outer logs scarred by dozens of impacts when the owners returned. The frontier geography shaped vulnerability. Isolated cabins stood on open prairie ridges and creek bottoms. Natural cover was minimal. Most farms lacked formal earthworks. The landscape offered attackers numerous concealed approaches through draws, tall grass, and broken ground. Defenders faced exposure from multiple directions. Weapons in common use defined the tactical environment. By the late 1860s, 50-70 government rifles had entered service, delivering a 450-grain bullet at roughly 1,260 feet per second muzzle velocity. The 45-70 government, introduced in 1873, fired a 405-grain bullet at similar velocities. Spencer and Henry repeating rifles, widely available as surplus after the Civil War, offered rapid fire, though with somewhat lower muzzle energy. Converted percussion muskets remained common. Ordnance records document muzzle energies ranging from 1,200 to 1,800 foot-pounds for these weapons. Effective ranges extended to 300-400 yards, though most frontier engagements occurred at 50-150 yards. Engagement geometry followed predictable patterns. Attackers fired from draws or grass cover, targeting doors, windows, and visible movement inside structures. The goal was often to pin defenders, prevent escape, or force surrender. Fire could be sustained for minutes or hours, depending on ammunition supply and tactical objectives. Standard log cabin construction provided the defensive baseline. Typical single-pen or double-pen layouts measured 12x14 to 16x20 feet, offering 1 or 2 rooms. Walls consisted of 6 to 8 inch round softwood logs, pine, cottonwood, or fir depending on local availability. Corner joints used saddle or V-notch styles. Chinking material was mud, clay, or scrap moss stuffed into gaps between courses. These materials improved weather tightness, but offered no ballistic protection. Roofs followed simple rafter systems covered with shingles or clapboards. Doors were constructed of 1-1-1/4-inch plank, usually unlined and unarmored. Windows, when present, were small openings fitted with simple shutters. Chimneys were mud and stick construction, or, less commonly, stone. Exposure and failure patterns appeared in raid narratives. County histories noted bullets passing through doors and upper wall courses, killing or wounding occupants behind them. The emphasis in survivor accounts on bullets coming through the logs and throwing splinters across rooms provided evidence that many walls fell within musket penetration capability. A Kansas County history recorded one raid. The house was shot full of holes, the door riddled, and splinters flew in all directions. The family took shelter behind a low stone wall inside and survived, though the cabin was ruined. The connection between 6 to 8-inch softwood thickness and military definitions was clear. By later engineering standards, these walls were not rifle-proof. The technical question emerged: what log size and species would have been required to stop the same black powder rounds at those ranges? 1st June 1864. Nebraska and Kansas frontier, forted up homesteads. A Nebraska history describes the Midway Cattle Company's 24-24 FT house, built of the heaviest and straightest cottonwood logs, and pierced with about 25 loopholes for defense against Indian attacks. Examples of fortified dwellings documented a different approach to frontier construction. In Jefferson County, Nebraska, the John Brown homestead served as a community refuge during the 1860s. The structure measured approximately 20-24 feet, with walls of 10-12-inch logs. In Washington County, Kansas, the Hollenberg Ranch Station combined commercial and defensive functions, with thick walls and deliberately placed firing positions. In Dakota Territory, the Fort Dilts site, actually a civilian refuge, not a military post, showed evidence of stockade construction using logs 8 to 10 inches in diameter set vertically. These structures differed from ordinary domestic cabins in their stated purpose. Sources explicitly described them as defensive, built with community protection in mind. They served as gathering points during periods of heightened threat. Timber stockades represented the clearest expression of defensive intent. The Gore Stockade on the Washita, constructed in 1874, used logs 20-30 feet long, set upright in a trench, 4 to 5 feet deep. This created an effective wall height of 15 to 20 feet. Log diameter ranged from 8 to 12 inches. A bullet striking such a wall encountered solid timber thickness approximating the log diameter, significantly more than the 6 to 8-inch thickness of horizontal log cabin walls, where corner notching and gaps reduced effective stopping power. Defensive detailing showed sophisticated understanding of tactical requirements. Loopholes were cut between logs with the upper log left intact, creating firing ports while maintaining wall integrity. Second stories or raised firing floors gave defenders downward fields of fire, making approach more difficult. Contemporary accounts described earth thrown up outside walls as additional protection and interior arrangements where sacks, goods, or furniture backed critical sectors against the possibility of bullet penetration. Terminology in local histories and reminiscences reflected this defensive awareness. Terms like bulletproof, rifle-proof, and forted appeared repeatedly. A Nebraska county history noted one structure. The logs were so thick that bullets stuck fast and could be dug out afterward as souvenirs. The contrast between isolated families in thin cabins and groups who concentrated heavy timber into defended buildings was stark. These log choices, 10 to 12 inches or more, closely matched thicknesses later specified in formal engineering tables. This suggested that some settlers, through experience or intuition, had overbuilt well into rifle-resistant territory without access to ballistic theory. The fortified structures represented a resource concentration strategy. Rather than attempting to make every dwelling defensible, communities identified 1 or 2 key buildings and invested scarce heavy timber there. This approach acknowledged both the genuine protective value of thick logs and the practical impossibility of building every cabin to such standards. 15th October 1867, mixed hardwood-softwood belt, central U.S. frontier. A frontier mill's lumber tally separates straight oak and hickory reserved for wagon parts and sills from a larger pile of pine and cottonwood slated for cabins and fencing. Species, selection, and wood density shaped both construction practices and ballistic performance. Engineering tables documented clear differences. White oak averaged 47 pounds per cubic foot, dry density. Hickory reached 51 pounds per cubic foot. Red oak measured 44 pounds per cubic foot. These compared with pine at 25 to 35 pounds per cubic foot, fir at 30-35 pounds per cubic foot, and cottonwood at 24 to 28 pounds per cubic foot. Hardness values followed similar patterns. Janka hardness tests, developed in the early 20th century, but reflecting inherent wood properties, showed hickory at 1,020 pounds force, white oak at 1,360 pounds force, and red oak at 1,290 pounds force. Eastern white pine measured only 380 pounds force. Ponderosa pine reached 460 pounds force. Cottonwood registered 430 pounds force. Ballistic penetration models and 20th century experiments confirmed what frontier builders might have intuited. Hardwoods required substantially less thickness than softwoods to stop a given projectile. The relationship was approximately linear with density. A hardwood log of 6 inches might provide stopping power equivalent to 10 to 12 inches of softwood. Competing uses for hardwood timber created economic pressure against defensive applications. Agricultural and construction manuals documented high-demand uses for straight, large-diameter hardwood. Wagon tongues required hickory or oak for strength and flexibility. Wheel hubs demanded dense hardwood to resist splitting under load. Axles and reach poles needed both strength and dimensional stability. Bridge timbers and foundation sills called for rot-resistant hardwoods. Fence posts of oak or locust outlasted softwood by decades. The economic calculation was straightforward. A single 12-inch oak log, 20 feet long, could be milled into wagon parts, tool handles, and furniture components representing significant value. The same log used in a cabin wall provided structural support and insulation, but added relatively little economic value compared to alternative uses. Many cabin builders defaulted to softer, smaller, or less uniform logs because the best timber commanded higher prices or served more critical purposes. Yet frontier anecdotes, imprecise and unverifiable as they were, suggested a tradition of picky builders who rejected this economic logic. Stories circulated about individuals who insisted on thick, straight heartwood for lower wall courses, rejecting crooked or sap-heavy logs, and being mocked as wasteful or foolish for the effort. A Nebraska reminiscence noted, "Old Schmidt spent 3 weeks selecting logs, while his neighbors built their cabins in days. They called him slow and particular beyond reason." These stories usually lacked verifiable names and measured log sizes. They functioned as folklore, carrying forward a memory of alternative construction philosophies. Here, they were treated as testable propositions rather than established facts. A period timber survey distinguished common logs, suitable for general construction, from select or prime logs reserved for critical structural elements, sills, corner posts, stockade pickets. The distinction acknowledged that not all timber was equivalent. The cultural calculus worked against defensive overbuilding. If a settler redirected rare, dense logs from wagons or bridges into cabin walls, neighbors saw waste of valuable resources. Ballistics suggested a potential gain in protection. But protection was probabilistic and future, while the economic loss was immediate and certain. Without direct experience of raids, most builders chose speed and economy. The challenge stood. Could documented measurements show that such foolishness, the deliberate selection of oversized, dense logs for cabin walls, plausibly turned a standard frontier dwelling into one that could actually resist contemporary rifle fire? May, 1888, British Army Field Fortification Tables, 19th to 20th century ballistics tests. A British field engineer's manual is open to the table headed "Protection against rifle bullets at any range." 2 ft of earth, 12 in of fir logs, 6 in of oak planks, and other materials in parallel columns. The 1888 British Manual represented the culmination of empirical ballistic testing conducted throughout the 19th century. The table listed required thicknesses for rifle-proof protection across multiple materials: earth, 24 inches, sand in bags, 12 inches, fir logs, 12 inches, oak planking, 6 inches, brick, 8 inches, stone, 3 to 4 inches, depending on type. These values applied to rifle bullets at any range, meaning they provided protection even at point-blank distances. The manual connected to earlier blockhouse literature and military engineering texts. A German military engineering manual from 1875 noted that a smoothbore musket ball could penetrate approximately 130 millimeters, roughly 5.1 inches, of ordinary pine wood at 100 meters. Rifled muskets with higher muzzle velocities achieved similar penetration at longer ranges. By the 1870s, breech-loading rifles with metallic cartridges had increased muzzle velocities and energies, necessitating thicker protection. Later 20th-century experimental work confirmed and refined these values. U.S. Army ordnance tests in the 1920s and 1930s measured penetration of various projectiles into different wood species. A .30-06 rifle bullet, substantially more powerful than black powder rifles, penetrated 14 to 18 inches of pine at 100 yards. Black powder rounds with lower velocities and energies showed proportionally less penetration. European ballistics research in the 1950s and 1960s established mathematical relationships between projectile energy, wood density, and penetration depth. The general scaling confirmed the 19th century empirical values, while stressing that modern high-velocity rounds penetrated much deeper. For black powder-era weapons, the British Manual's figures remained valid benchmarks. Translating engineering tables to log cabin practice required careful interpretation. The 12 inches of fir specified in the table corresponded to a continuous section of fir timber 12 inches thick. In a log cabin wall, a 12-inch diameter fir log provided approximately that thickness through most of its cross-section, reduced somewhat at the top and bottom of each log, where curvature diminished effective thickness, and at corners where notching reduced material. A 10-12-inch hardwood log roughly equaled or exceeded the 6-inch oak plank standard over most of its section. The round profile actually provided more thickness than flat planking when bullets struck at oblique angles, as the curved surface increased the effective path length through the wood. Implications for typical 6 to 8-inch frontier cabins became clear. Compare a 7-inch softwood wall with the 5-inch penetration figure for musket fire at 100 meters. The safety margin was only 2 inches, well within the range of variation caused by knots, checks, sapwood versus heartwood, and impact angle. At perpendicular impact, at close range, or where logs were thinner or of lower quality, penetration was likely. Where logs were 6 inches or less, as in many upper courses or near notches, penetration was probable. The quantitative boundary was precise, moving from 7-8-inch softwood to approximately 12-inch softwood or 6-inch hardwood, crossed the line from within expected penetration depth to rifle-proof by contemporary military engineering criteria. This was exactly the design space where unusually thick or dense log selection would produce measurable protective advantage. 8 August 1866, Central and Northern Plains cabins. A pioneer building manual diagram shows a single pen cabin with 7 to 8 log courses, a mud chimney on one gable end, and a thin plank door on leather hinges. Measured wall geometry from architectural surveys and cabin reconstructions established typical dimensions. Log diameters commonly ranged from 6 to 9 inches for softwood species. Wall heights of 7 to 8 feet required 8 to 10 log courses depending on log diameter and settling. Corner notches consumed 1 to 3 inches of log length on each end, creating zones of reduced thickness at every corner. Saddle notches, the most common style, involved cutting a rounded depression in the top of each log to receive the log above. This created a reasonably tight fit, but left gaps that required chinking. V-notches cut angular grooves into log ends, creating interlocking corners but removing significant wood volume. Each notch reduced effective wall thickness in that zone by 30–50% compared to mid-span sections of the same logs. Diagrams from period construction manuals illustrated how these joints performed structurally. They handled vertical loads well, transferring weight from upper courses through to sills and foundation. But from a ballistic perspective, they created vulnerability. A bullet striking within 12 to 18 inches of a corner might pass through only 3 to 5 inches of effective wood rather than the full log diameter. Gaps, shrinkage, and settling compounded these weak points. Newly built cabins with green logs could settle 6 to 12 inches in the first year, as wood dried and compressed. Longitudinal shrinkage was minimal, but radial shrinkage, perpendicular to growth rings, could reduce log diameter by 5 to 10%. Gaps reopened between courses. Logs pulled apart at corners. Careful builders countered this with door and window frames that floated rather than being fixed, allowing settlement without binding. Chinking improved weather tightness dramatically. Mud, mixed with grass or straw, clay, or moss stuffed into gaps, kept wind and rain out. But these materials contributed negligibly to ballistic resistance. A bullet passing through a 1-inch gap filled with mud chinking encountered no meaningful obstacle. The log wood itself provided all the protection. Doors, windows, gables, and chimneys represented obvious vulnerabilities. Door plank thickness of 1–1–1–4 inches fell well below the 5-inch musket penetration threshold. Period military tests showed that a black powder rifle ball at 100 yards could penetrate 2 inches of pine planking, pass through a typical door, and retain lethal energy on the other side. Historical raid accounts consistently reported penetrations through doors. One Kansas account noted, "The door was struck 17 times and pierced through in 9 places." Window openings, even when shuttered, provided minimal protection. Shutters were typically 3–4 to 1-inch boards, offering no ballistic resistance. Gable end walls used lighter boards, wattle and daub, or thin logs to close the triangular space between wall top and roof peak. These sections stopped wind, but not bullets. A Nebraska homesteading guide from 1872 prescribed log sizes for speed and economy. Select round logs of 6 to 8 inches, as straight as available. Notch simply at corners. Roof with boards and tar paper. A family can raise such a cabin in 4 to 6 days with neighbors' help. The guidance prioritized speed over strength. It made no mention of defensive considerations. Even with nominal 8-inch logs, many sightlines through a cabin presented only 4 to 6 inches of wood, through corners, around openings, under eaves where logs tapered, or where checks and splits had opened. These dimensions aligned precisely with the musket penetration depth of 5 inches. Typical frontier cabins were never designed as ballistic structures. They were designed for weather protection, erected quickly with available materials. This explained the riddled walls described in raid accounts. The walls performed as built, adequate for daily life, inadequate for combat. 3rd September 1874, Indian War frontier. Stockades and fortified houses, a historical description of the 1874 Gore Stockade on the Washita notes, logs 20–30, ft long set upright, 4 to 5 ft into a trench, forming a palisade that sheltered 19 people. Several well-documented events provided case studies of successful defenses in log or timber structures. The Gore Stockade, September 1874, withstood a sustained attack by approximately 100 to 150 Kiowa and Comanche fighters over several hours. Defenders numbered 19 men, women, and children. The attackers used rifles, documented in reports as a mix of military arms and trade weapons. Duration was estimated at 4 to 6 hours until the attackers withdrew. Wall configuration at Gore followed standard stockade practice. Vertical logs, 8 to 10 inches in diameter, set in a trench creating 15-20 feet of exposed height. Contemporary accounts noted that bullets struck and lodged in the timber, and that defenders found many balls embedded in the logs afterward, which they kept as souvenirs. The Hollenberg Ranch Station on the Oregon Trail, fortified in the 1850s and 1860s, featured horizontal log walls of 10 to 12-inch cottonwood. The structure served as both residence and way station. During threats, neighboring families gathered there. A reminiscence noted, "The walls were thick enough that when Indians fired upon the place in '64, not one ball came through to the inside, though the outer logs bore many marks." At adobe walls in the Texas Panhandle, June 1874, buffalo hunters defended sod-roofed log buildings against several hundred attackers over multiple days. The structures had been built for commerce, but featured unusually thick walls, 12 16-inch logs, and, in some sections, double walls. Accounts credited the heavy construction with preventing casualties during initial volleys that killed horses in the compound but failed to penetrate the buildings. Contrasting failures provided the comparison. At the same adobe walls site, a small outbuilding of lighter construction was shot to pieces and abandoned immediately. In Nebraska, the 1869 attack on a homestead with 6-inch log walls resulted in deaths inside the cabin, when balls came through the upper courses and struck the family huddled behind a table. One pattern repeated. Defenders who relocated from vulnerable structures to stouter ones on the same site survived. A Kansas incident in 1867 involved a family initially in a plank house who, once firing started, ran to a nearby cattle shed built of heavy timbers. The plank house was perforated 40 times, while the shed, though struck repeatedly, showed balls lodged in the timber, but none passed through. Archival evidence explicitly credited thick walls. A Texas county history recorded, "The stockade logs, being green cottonwood of great size, stopped the rifle balls, which the defenders later dug out. This saved many lives." The documentary record showed a measurable pattern. Where settlers invested heavy timber, 10 to 12 inches or more in continuous walls, structures performed differently under fire than lighter buildings. Bullets lodged rather than penetrating. Interior spaces remained relatively safe. Defenders could maintain positions near walls without lethal risk. These cases effectively validated the protection levels later quantified in formal military engineering tables. The settlers who built Gore Stockade, Hollenberg Station, and the adobe wall structures had no access to British field manuals. Yet their log selections and wall thicknesses matched. Within the margin of natural variation, the dimensions engineers would later specify as rifle-proof. Experience and observation, transmitted through frontier networks and military-civilian interaction, had generated practical ballistic engineering. 15th of March, 2024. Analytical reconstruction using 1860s data. On a drafting table, 2-wall cross-sections are drawn at equal scale. A standard 7 in pine log wall beside an 11 in hardwood wall, each with its corner detail sketched. The analytical reconstruction acknowledged its limitations at the outset. No full measured plan existed for a named Bulletproof 1860s frontier cabin. No diary entry specified, I selected 12-inch oak logs for ballistic protection. The following reconstruction was synthetic, assembled from documented cabin construction records, stockade descriptions, and engineering ballistics tables. The goal was to model a plausible upper-end civilian defensive wall, not to claim that any specific homestead looked exactly this way, but to test whether the physics and materials supported the folklore. The standard wall served as baseline, 7 8-inch round softwood logs, single thickness, saddle-notched corners, mud chinking, no inner lining or backing. This matched the documented norm from homesteading guides, archaeological surveys, and construction manuals. A specific instance might use 7.5-inch ponderosa pine logs, saddle-notched with 2-inch deep cuts at corners, chinked with clay and grass. Wall height, 7.5 feet from sill to plate, requiring 9 logs averaging 8 inches in height per course. Total log count for a 16-ack 20-foot cabin, approximately 72 logs. The overbuilt wall specification departed from this norm in several dimensions. Log diameter, 10 to 12 inches of hardwood or dense softwood. Species, white oak, red oak, or Douglas fir rather than pine or cottonwood. Log quality. Rejection of logs with large knots, checks, or excessive sapwood in the lower 4 courses, where bullet impacts were most likely. Hewn interior face. The inside of each log was flattened with an adze or broadaxe, creating a smooth surface and maximizing wall thickness at the interior face where bullets exited. Double-notched corners. Rather than simple saddle notches, corners used a more complex joint that maximized overlap, reducing the zone of decreased thickness at each corner. Interior sheathing, optional but documented in some forted structures. A secondary wall of vertical planks or a stud frame at shoulder height, the void partially filled with earth, sand, or stone. Ballistic performance comparison mapped these sections against established requirements. The standard 7-8-inch softwood wall fell below the 12-inch fir 10-inch pine threshold for rifle-proof protection and marginally exceeded the 5-inch musket penetration figure, only at mid-span in soundwood, not at corners or near openings. The overbuilt wall provided 10-12 inches of hardwood or dense softwood through most of its section. At corners, the double-notch style maintained 8 to 10 inches even in the joint zone. The hewn interior face eliminated the natural taper of round logs at top and bottom, maintaining maximum thickness. If backed with earth or stone, fill between an inner stud wall, effective thickness increased to 14-18 inches in critical zones. This met or exceeded the British manual's fir log and oak plank standards. A perpendicular bullet strike at mid-span encountered 10-12 inches of continuous dense wood, double the 5-inch musket penetration figure and matching the 12-inch fir specification. Even oblique strikes, which increased effective thickness, or strikes near corners, which reduced it, remained within the rifle-proof band. Historical linkage to documented structures supported the reconstruction. The Midway Cattle Company's defensive house in Nebraska was described as using the heaviest and straightest cottonwood logs, language implying selection for size and quality. The Gore stockade used 8 to 10-inch logs set vertically, providing approximately 10 inches of stopping thickness. Adobe wall structures ranged from 12 to 16 inches. These were not typical cabins, but represented the achievable upper bound using frontier resources and hand tools. A quantitative summary made the comparison stark. The overbuilt wall provided roughly 50-100% greater effective stopping thickness than a common wall. A 7-inch pine wall offered 7 inches at best, 4 to 5 inches at corners and weak points. An 11-inch oak wall offered 11 inches at midspan, 8 to 9 inches at corners, fitting neatly into the rifle-proof band defined by late 19th century military engineers, even if no one on the 1860s frontier had run those calculations. The cost of such construction was significant. Felling, transporting, and placing a 12-inch oak log required substantially more labor than a 7-inch pine log. The weight ratio was roughly 1.3. An 11-inch log, 20 feet long, weighed approximately 600-800 pounds depending on species and moisture content. A 7-inch pine log of the same length weighed 200-300 pounds. Selective cutting for quality added time. Hewing interior faces demanded skilled labor. Corner joinery complexity doubled the time per corner. A standard cabin might be raised in 4 to 6 days with help from neighbors. An overbuilt cabin following these specifications might require 12 to 15 days. But the ballistic advantage was equally quantifiable. Where a standard cabin offered survival only by luck, bullets might penetrate or might not, depending on exact impact location. An overbuilt cabin offered survival by design, with predictable protection across most wall sections. 12 of April, 1871, 1920. Raid reports and ballistic observations. A post-raid account describes not only bullet-scarred walls, but holes in the shaken roof, broken rafters, and shattered window frames that now admit rain and light. Roof vulnerability represented a critical weakness even in cabins with thick walls. Typical frontier roofs used 1-2-inch boards or split shingles over rafters. Occasionally, builders added brush and earth for insulation, but even earth-covered roofs rarely exceeded 4 to 6 inches total thickness. These dimensions fell well below the 5-inch penetration depth for musket balls. Tests, conducted by military engineers in the 1870s, showed that a .45-70 rifle round fired at a 45-degree angle could penetrate 3 inches of pine roofing, pass through a 6-inch air gap, a typical attic or loft space, and strike the ceiling below with lethal force. Vertical or near-vertical fire, possible from elevated positions or when attackers climbed nearby trees or slopes, could penetrate roofs with ease. Historical accounts documented this vulnerability. A Colorado raid account from 1879 noted, "Rifle fire from the ridge above pierced the cabin roof in several places. One ball passed through the roof and ceiling, striking a child in the arm." A Wyoming incident recorded, "The shake roof offered no protection. Defenders were forced to crowd against the north wall, where the roof angle blocked direct fire from the south ridge." Openings and splinters created additional hazards, even when walls themselves held. Bullets striking door frames and window casings produced dangerous splinters. The impact of a rifle ball on seasoned oak or pine framing timber could throw foot-long splinters with enough force to cause serious injury. Interior splintering from near penetrations appeared in multiple accounts, suggesting that even thick logs, when struck by heavy rounds at close range, could throw interior spalling without full penetration. One Texas account described, "A ball struck the doorframe and sent splinters across the room. One fragment struck my father in the face, laying open his cheek, though the ball itself did not enter." Ricochet and angle effects complicated interior ballistics in unpredictable ways. Experimental notes from military proving grounds showed that round-nosed lead bullets could glance off rounded log surfaces at shallow angles. A bullet striking a horizontal log at 15-20 degrees from parallel might deflect upward or downward rather than penetrating. But perpendicular hits penetrated most deeply, and impacts at intermediate angles, 30 to 60 degrees, sometimes tumbled, creating irregular wound channels in the wood, and unpredictable paths if they reached interior space. Notched corners and irregular log placement created zones where ricochets were more likely. A bullet striking near a corner might deflect off one log onto another, its path bent, but energy only partially dissipated. Inside cabins, the irregular surface of unhewn logs, protruding chinking, and furniture placement created countless deflection possibilities. Military engineers testing interior ballistics in mock-up rooms found that predicting ricochet paths was nearly impossible except in highly controlled conditions. Documented countermeasures showed that frontier defenders understood these vulnerabilities and adapted. Closing and barricading windows with interior furniture or stacked goods appeared in numerous accounts. "We piled sacks of grain against the door and windows on the exposed side, leaving only firing slits. Hanging extra planks, hides, or mattresses behind doors reinforced the weakest points. Mother hung our feather ticks on the inside of the door and windows, which stopped several balls that came through the planking. Placing sod or earth on roofs during threatened periods addressed overhead vulnerability. This practice, documented in several frontier diaries, involved piling 6 to 12 inches of earth onto existing roofs. The added weight stressed roof framing, but significantly increased ballistic protection. A settler in Kansas noted, "When reports came of troubles, we shoveled earth onto the cabin roof until it would bear no more, which gave us peace of mind against high fire." Log selection improved wall segments, but could not alone make a cabin a complete defensive system. The strongest wall mattered little if fire came through the roof, door, or windows. Conversely, the best protected openings offered limited advantage if wall logs were too thin. A truly protective dwelling required addressing all weak points simultaneously: roof, openings, corners, and wall thickness. This systemic approach appeared in the forted structures that successfully defended occupants. It rarely appeared in ordinary homesteads, where defensive construction competed with dozens of other priorities and resource constraints. The Gore stockade, for instance, combined thick vertical logs with an earth-banked exterior wall at the base, minimal openings placed high in the wall, and a roof built in sections that could be quickly covered with earth if needed. Adobe wall structures used sod roofs from the outset, providing overhead protection integrated into initial design. The Hollenberg station featured interior shutters backed with sand-filled grain sacks, and a heavy plank door with crossbar reinforcement. Each element addressed a specific failure mode. The lesson was clear: ballistic protection was a system property, not a component property. Superior log selection was necessary, but not sufficient. It established the defensive foundation, but required complementary measures at every vulnerable point to achieve true protection. Modeled scenario based on 1870s ballistics. A comparative table shows two columns: standard 7 and 8 in softwood wall, and overbuilt 11 to 12 in dense wall, with rows for shots fired, estimated full penetrations, and bullets lodged. The modeled scenario defined a representative attack based on documented frontier engagements. Several riflemen, assumed to be 5 to 7 individuals, positioned at approximately 100 yards, firing a total of 100 shots over 3 to 5 minutes at exposed wall sections. This firing rate, roughly 1 shot every 2 to 3 seconds across all shooters, matched capabilities of single-shot breech-loading rifles with prepared ammunition. Attackers targeted visible wall sections, doors, windows, and areas where movement or light suggested defender positions. Projectile specifications followed period rifle data. A .45-70 government rifle fired a 405 grain lead bullet at approximately 1,350 feet per second muzzle velocity. At 100 yards, velocity had dropped to roughly 1,150 feet per second. Kinetic energy, approximately 1,200 foot-pounds at muzzle, 1,000 foot-pounds at 100 yards. Bullet construction, soft lead with round or flat nose. These ballistic parameters applied to the most common military and civilian rifles of the 1870s. For the standard wall, 7.5-inch pine logs, comparison with the 1888 table and penetration curves indicated vulnerability. The 12-inch fir standard implied that 7.5 inches fell significantly short. Empirical penetration data showed musket balls penetrating 5 inches at 100 meters. The 45-70, with higher energy, could be expected to penetrate 6 to 7 inches of pine under perpendicular impact. At 100 yards, energy was sufficient to fully penetrate a 7.5-inch log at perpendicular impact or near perpendicular angles. Incorporating obliquity adjusted the estimate. Not all 100 shots struck perpendicularly. A distribution of impact angles was assumed. 40% of shots at 75 to 90 degrees, nearly perpendicular, 40% at 45-75 degrees, oblique, and 20% at less than 45 degrees, highly oblique or glancing. Effective thickness increased with obliquity. A bullet, striking at 60 degrees to the surface, normally encountered roughly 1.4 times the nominal log thickness. A bullet at 30 degrees encountered roughly 2 times the thickness. For the standard cabin, estimated full penetrations of 100 rounds, approximately 30-40, might fully penetrate wall logs where they struck midspan at perpendicular or near perpendicular angles. Another 20-30 might lodge partway through the log, stopping before reaching the interior surface, but visibly bulging the wood inward. The remaining 30 to 50 rounds might strike at angles shallow enough to deflect, lodge near the surface, or hit corner zones, window frames, or the door, which offered even less protection. Interior risk from 30-40 full penetrations was severe. Occupants standing or moving near walls faced direct bullet strikes. Those at the room center faced ricochets, spalling, and splinters. The cabin's small size, perhaps 16 how 20 feet or 320 square feet, meant few areas were truly protected. For the overbuilt cabin, 11-inch white oak logs, the calculation changed fundamentally. The British table specified 6 inches of oak planking as rifle-proof. An 11-inch oak log exceeded this by 80%. Empirical data suggested that 45-70 penetration into oak at 100 yards would be approximately 7 to 8 inches under perpendicular impact. An 11-inch log provided a safety margin of 3 to 4 inches. Of 100 rounds fired, estimated full penetrations, approximately 5 to 10, occurring only where shots struck at exactly perpendicular angles, at thinner sections near the top or bottom of logs, or at corners where even the improved joinery reduced effective thickness to 8 to 9 inches. Most shots, 60-70 of 100, lodged within the log, stopped well short of the interior surface. The remaining 20-30 deflected at shallow angles or struck openings. The comparison was stark. The standard wall allowed dozens of potential through shots. The overbuilt wall reduced that to a small handful, and those few penetrations were limited to specific vulnerable zones that could be identified and avoided by defenders. Openings complicated both scenarios. Any shot through an unarmored door or window bypassed wall thickness entirely. A 1.25-inch plank door stopped nothing. This reality check confirmed that even the best wall selection couldn't fully protect a cabin without addressing doors, windows, and roof. But the headline comparison quantified, in practical terms, what frontier folklore meant when it said one house stood the fire better than its neighbors. Under identical attack scenarios, same number of shots, same range, same weapons, the overbuilt cabin's occupants faced perhaps 1/5 the interior risk of the standard cabin's occupants. That difference, measured in expected penetrations per 100 rounds, translated directly to survival probability. The 1888 Protection Against Rifle Bullets table lies next to the overbuilt wall drawing. Lines connect fir logs, 12 in, and oak planks, 6 in, to the log diameters used in the reconstruction. The folklore pattern could now be restated precisely. An anonymous frontier story suggested a settler mocked for insistence on thick, straight logs, whose cabin later withstood rifle fire better than neighboring houses. No archival case had been found that named this settler, specified exact log dimensions, and documented bullet performance. The story pattern appeared in multiple regional variations, but always lacked verifiable detail. It was treated here as a testable hypothesis rather than historical fact. The direct comparison with engineering standards provided the test. An 11-12-inch dense softwood wall, Douglas fir, longleaf pine, satisfied or exceeded the rifle-proof threshold in the 1888 table. The table specified 12 inches for fir. An 11-inch fir log fell only 8% short, and, given natural variation in log taper and the conservative nature of military specifications, effectively met the standard. A 10-12-inch hardwood wall clearly exceeded the 6-inch oak plank standard. A 10-inch white oak log provided 67% more thickness than specified. An 11-inch oak log exceeded the requirement by 83%. A 12-inch oak log doubled it. The key was that a good portion of such a wall behaved like continuous timber of the specified thickness when free from major defects. Defects mattered, and sensitivity analysis had to account for them. Knots reduced density locally and could deflect bullets unpredictably, sometimes stopping them more effectively through energy dissipation in fractured wood, sometimes creating channels for penetration. Checks and splits created planes of weakness. Sapwood, less dense than heartwood, offered less resistance. Gaps between courses, even when chinked, represented zero-thickness zones. A realistic overbuilt wall, despite careful log selection, might have 5 to 10% of its surface area compromised by defects. In the zones affected, effective thickness dropped to perhaps 70–80% of nominal. An 11-inch oak log with a 2-inch check might offer only 9 inches of sound wood across that check line. This was still well above the 6-inch standard, but represented a local reduction in safety margin. The shot angle worked in the wall's favor. Oblique hits increased effective thickness. A bullet, striking an 11-inch log at 60 degrees, encountered roughly 15.4 inches of wood, 11 chasacurcus 30 degrees. Bullets, striking at 45 degrees, encountered 15.6 inches, 11 cus 45 degrees. Only perpendicular or near-perpendicular shots challenged the wall at its nominal thickness. Given that many shots in actual engagements struck at oblique angles due to firing positions, terrain, and log curvature, the practical performance band was wider than the nominal calculation suggested. The performance band conclusion was clear. By 19th century engineering definitions, an overbuilt wall of 10 to 12-inch hardwood, or 11 to 13-inch dense softwood, fell into the rifle-proof category for black powder rifle threats. It met or exceeded the formal military specifications derived from extensive empirical testing. Ordinary cabin walls of 6 to 8-inch softwood did not. They fell within the penetration envelope for musket fire and marginal for rifle fire. The factual paradox could now be stated precisely. Judged by engineering standards published in 1888, but based on tests conducted throughout the 1860s and 1870s, contemporary with frontier settlement, the foolish builder's wall met formal rifle-proof criteria. The faster, cheaper cabins that neighbors praised and that predominated across the frontier did not. The mockery was socially rational. Why waste time and scarce hardwood on excessive construction, but ballistically backward? The foolish choice was technically correct. This did not prove that any specific frontier cabin was bulletproof, or that any specific settler was mocked for log selection and later vindicated by a raid. It proved that the ballistic physics and material properties supported such an outcome if it occurred. The folklore, even if it preserved no specific documented case, was ballistically plausible. The stronger claim was that documented defensive structures, Gore Stockade, Adobe Walls, Hollenberg Station, the Midway Cattle Company House, demonstrated that frontier builders, through experience and observation, had converged on log selections matching engineering specifications they never saw. This convergence suggested a transmission of practical ballistic knowledge through frontier networks. Veterans of military fort construction, working as civilian builders, former soldiers advising on defensive preparations, and survivors of raids sharing specific lessons about what had and hadn't stopped bullets. A chart compares Cabin A, standard, and Cabin B, overbuilt, across 3 rows. Expected interior hits, safe interior area, and time under effective shelter. From penetrations to safe space, the Chapter 9. Penetration estimates could be translated into interior geography. In the standard cabin, with 30 to 40 expected full penetrations from 100 rounds, and no way to predict exactly where those penetrations would occur. Essentially, no interior zone was safe. Occupants standing near any wall section faced risk. Those at the room center faced ricochets and flying debris. A crude spatial analysis divided the interior into zones. Against each wall, a zone of 2 feet depth was high risk, direct line to bullet paths. The room center, perhaps 8 feet by 12 feet, was medium risk, indirect fire only. But in a sustained engagement with hundreds of rounds, even the center became dangerous as ricochets and spalling accumulated. In the overbuilt cabin, with only 5–10 expected penetrations from 100 rounds, and those concentrated at predictable weak points, doors, windows, upper courses, specific corner zones, interior risk geography changed. Zones directly opposite doors and windows remained high risk. But large wall sections, those using the thickest logs at midspan height, became low risk. Occupants could stand near these walls, fire out through loopholes, and move with reasonable confidence. The safe interior area calculation was approximate, but telling. Standard cabin, perhaps 40% of floor area offered medium risk, 0% offered low risk. Overbuilt cabin, perhaps 60% of floor area offered medium risk, 30% offered low risk. This meant defenders could use more of the structure, maintain better firing positions, and avoid being crowded into corners or cellars. Duration of viable defense connected to historical raid narratives. Engagements where defenders held out until attackers withdrew or relief arrived typically lasted hours to days. The adobe walls siege lasted several days. Shorter raids ended when attackers judged the cost too high or perceived reinforcements approaching. Thicker walls extended the period defenders could remain in position without being driven out by casualties or terror. A psychological dimension appeared in accounts. Defenders in stout houses expressed confidence. We knew the walls would hold. Defenders in thin structures described terror. Each shot that struck might come through. This psychological factor affected tactical decisions, whether to fight or flee, whether to hold position or crowd into one corner, whether to return fire or simply shelter. Secondary effects from fewer penetrations reduced multiple risks. Interior fires from burning wads or hot bullets igniting fabric and furnishings were less likely. Structural integrity was preserved. Fewer bullets striking load-bearing members meant less chance of catastrophic failure. Flying debris, splinters, and lead fragments were reduced in proportion to hits. One Kansas account captured the relief. We sheltered in the Johnson place, built of thick logs. Balls struck like hail, but none came through. We felt safe behind those logs, though the firing went on for an hour. The contrast with terror in vulnerable structures was stark. A Colorado account. In the thin cabin, my mother clutched us behind the table while balls came through the walls. She prayed and wept, certain we would die. An archival fragment provided the summation. A Nebraska county history recorded a successful defense. The McAllister Stockade, built of cottonwood logs 10 to 12 inches thick, withstood a sustained attack in August 1867. 19 souls took shelter there. Though the logs were struck many times, none of the balls penetrated to the interior. The occupants credited the thickness of the timber with saving their lives. The survival margin could be stated plainly. Under comparable volumes of fire, an overbuilt wall significantly increased the likelihood that all occupants survived and remained capable of defense. The extra inches of wood, 4 to 5 inches more than standard, carefully selected for density and quality, showed up as a measurable survival margin. It was not a construction preference or an aesthetic choice. It was the difference between 30 penetrations and 5, between terror and confidence, between probable casualties and probable survival. In the calculus of frontier risk, these margins were everything. A single penetration that killed or wounded a defender reduced the defensive capability of the entire household. A family of 4 adults could maintain effective defense. A family reduced to 3 by a casualty, with 1 adult tending the wounded, could not. The cascade from one penetration to tactical collapse could be swift. The overbuilt wall delayed or prevented that cascade. It was insurance measured in inches of oak, purchased with extra labor in log selection and placement, paying its premium in the form of neighbors' mockery, and collecting its benefit in the unlikely but catastrophic event of sustained rifle fire. For families who never faced an attack, the premium was pure cost. For the few who did, the benefit was survival. 1870-1920. Western Frontier and Post-Frontier. A photographic sequence shows an early blockhouse with loopholes, a nearby ordinary homestead cabin, and, decades later, both structures collapsing back into the landscape. resource, and labor costs made defensive construction prohibitively expensive for most settlers. Quantifying the difference clarified why. Felling a 12-inch hardwood tree required significantly more axe work than a 7-inch softwood tree. Time ratio, roughly 2.5.1. A skilled axeman might drop a 7-inch pine in 30 to 40 minutes. A 12-inch oak took 75 to 90 minutes. Transport compounded the difference. Weight increased with the cube of diameter. A 12-inch log 20 feet long weighed 700 to 900 pounds. A 7-inch log of the same length weighed 250, 350 pounds. This meant that moving 12-inch logs required oxen, horses, or multiple men with cant, hooks, infrastructure, and cooperation not all settlers possessed. Stacking and placing heavy logs increased labor per course. 2 men could lift a 7-inch pine log into position using peavies. A 12-inch oak log required 4 men and often block and tackle rigging. Corner notching for heavy logs demanded greater skill and precision. The accumulated time penalty for an overbuilt cabin of 10 12-inch logs versus a standard cabin of 7 8-inch logs was approximately 150 to 200%, assuming equal skill levels. Many families had limited manpower. A household of 1 or 2 adults, with young children, relied on neighbors for cabin raising. Neighbors donated labor with the expectation of reciprocity. Asking neighbors to spend 3 days on an overbuilt cabin when 1 day sufficed for a standard cabin created social debt. The economics made defensive overbuilding viable only for wealthy cattle companies, cooperative groups pooling labor, or individuals with exceptional resources and determination. Rapid shelter was essential. Arrival on a claim in spring meant a race to establish dwelling, break ground, plant crops, and secure provisions before winter. Every day spent on cabin construction was a day not spent on food production. The calculus favored speed. A family that spent 2 weeks building an overbuilt cabin might face food shortages that winter. A family that spent 1 week on a standard cabin and 1 week on crops had better survival odds, provided raids didn't occur. The evolving threat profile shifted incentives over time. The spread of military forts, railroad construction, and treaty agreements reduced perceived Indian raid risk in many regions within a decade or two. In Kansas and Nebraska, peak threat periods were the 1860s and early 1870s. By the 1880s, the frontier had moved west, and military control was established. In Montana and Dakota territories, threat periods extended into the 1870s and early 1880s, then declined rapidly after major military campaigns. Settlers making construction decisions in, say, 1885 in eastern Kansas had little expectation of raids. Those making decisions in 1867 did, but the 1867 settlers couldn't know when the threat would recede. Building defensively hedged against future risk, but if raids never came, the investment was lost cost. Information and culture shaped perceptions and habits. Frontier builders generally lacked access to formal engineering tables. Construction knowledge was transmitted orally, through observation of existing buildings, and from pattern books that emphasized weather protection and economy. Defensive considerations appeared in military manuals and some frontier guides, particularly those published in the 1860s and early 1870s, but few settlers consulted such texts. In memoirs, moving from a dugout or blockhouse to a lighter frame house was often framed as progress, with little mention of reduced ballistic protection. An 1890 Nebraska reminiscence noted, "We abandoned the old, stockade house in 75, once the Indian troubles ended, and built a fine frame dwelling with glass windows and painted siding. It was a mark of how far we had come." The statement revealed priorities. Weather protection, comfort, light, aesthetics, and social status outweighed defensive capability once immediate threat subsided. The frame house with glass windows was objectively less defensible than the stockade, but subjectively superior in every dimension that mattered for daily life. An archival fragment captured the transition. A Kansas settler wrote in 1878, "The forted cabin, built in '67 when we feared attack, now seems gloomy and rough. We plan a new house this year, light and cheerful, for we no longer need to live like men at war." Bullet-resistant construction emerged only where high threat, adequate timber, and unusual foresight aligned. The Gore Stockade was built in 1874 in response to specific intelligence of planned attacks. Adobe wall structures were commercial buildings in an isolated location with a recent history of conflict. The Midway Cattle Company House served as a company headquarters with valuable assets to protect. Each represented unusual circumstances, not typical homesteading. The frontier never codified a rifle-proof cabin standard for ordinary homesteads, despite military knowledge that could have supported it. The military built forts with specific defensive features. Civilians built homes optimized for a different set of requirements. The two building traditions overlapped at the edges in forted structures and community refugees, but remained largely separate. A modern section drawing overlays log diameters and species labels on a cabin wall, with the 1888 fir log and oak plank rifle-proof figures annotated in the margin. Key design rules drawn from historical analysis offered a template for black powder rifle threats similar to those of the 19th century. Target approximately 12 inches of fir or comparable softwood, or 6 inches of sound hardwood, in continuous thickness through wall sections. These specifications, derived from the 1888 British Manual and validated by documented defensive structures, provided rifle-proof protection against .45-70 class weapons at any range. Maintain tight corner notching and overlap. The double notch or full dovetail corner style maximized effective thickness in corner zones. Avoid thin log ends where taper reduced diameter below the protective threshold. Gap between courses should be minimized through careful fitting, with chinking serving to seal air gaps rather than to fill large voids. Reinforce doors and windows, as these remained the weakest points, even in thick-walled structures. A door of 2-inch oak planking, or double planking with a sandbag backing, approached adequate protection. Interior shutters backed with earth-filled sacks provided window protection without sacrificing light during non-threat periods. Consider internal backing at key positions. A half-height stone or earth-filled wall inside the cabin, shoulder height, created protected zones for defenders to crouch behind. This doubled effective thickness in the backed zones and provided fallback positions if outer walls were compromised. Limits with modern weapons required explicit statements. The dimensions adequate for black powder rifles were not adequate for modern high-velocity centerfire rifles. A .30-06 rifle, typical of early 20th century military arms, delivered approximately 2,800 foot-pounds of muzzle energy versus 1,800 foot-pounds for a .45-70. Velocities were 2,700 feet per second versus 1,350 feet per second. Penetration scaled roughly with kinetic energy, meaning a .30-06 could penetrate perhaps 18-22 inches of pine, far exceeding the 12-inch black powder standard. Modern military rifle rounds. Joint 308 Winchester 5.56 45 mm NATO 7.62 chest 39 mm, varied in energy, but all exceeded black powder levels. Armor-piercing ammunition, steel core projectiles, and specialized penetrators further increased capability. No practical thickness of timber provided rifle-proof protection against modern military arms. The principles remained valid. Thickness, density, and continuity governed resistance. A wall twice as thick stopped more than a wall half as thick. Dense wood stopped more than light wood. Continuous timber stopped more than gapped or defective timber. The physics didn't change. The projectile energy did. For historical reenactors, living history sites, or individuals interested in frontier-accurate defensive construction, the specification was straightforward. Use 11-13-inch diameter dense softwood, or 10-12-inch diameter hardwood for lower wall courses. The interior faces flat. Use double-notch corners. Reject logs with large knots, checks, or rot. Back critical zones with earth-filled timber cribs. Reinforce doors and windows. The result would match, as closely as practical with modern safety standards and building codes, the performance characteristics of the rare frontier defensive cabins that successfully protected occupants under fire. A concise quantitative takeaway summarized the historical lesson. Increasing log diameter from 6 to 8 inch common softwood to 12-inch dense softwood, or to 6 to 10-inch hardwood. Reduced through penetration probability from 19th century rifles by roughly an order of magnitude. Where a standard cabin might experience 30-40 full penetrations from 100 rounds at 100 yards, an overbuilt cabin might experience 3 to 5. That tenfold reduction, implied by historical engineering tables and validated by case comparisons, represented the measurable survival advantage purchased by careful log selection. This was the engineering backbone behind the old story of the foolishly picky builder whose walls held when others failed. The story might not preserve a verifiable name or date, but it preserved a technical truth: that log selection mattered, that measurements determined outcomes, and that what neighbors called waste was, in ballistic terms, investment in survival. The frontier taught many lessons in the relationship between material choices and survival. This was one. In the calculus of frontier defense, inches of dense wood converted directly to safety margins. Where standard practice provided walls that barely exceeded musket penetration depth, a commitment to heavier, denser logs pushed those walls into the rifle-proof category documented by military engineers. For the hundreds of thousands of frontier families who built standard cabins and never faced attack, the extra labor and cost of defensive construction would have been wasted. For the hundreds who did face attack in thin-walled cabins, the lack of that investment cost lives. For the handful who built defensively, whether through foresight, paranoia, or accident, and then faced attack, the investment paid the highest return: survival. That return was measurable in the accounts of bullets lodged in thick logs, of families sheltered safely behind 12-inch timber walls while rifle fire struck from outside, and of defenders who afterward dug spent bullets from their cabin walls as souvenirs of the day when wood thickness, carefully selected and precisely placed, made the difference between casualty and survival. If you value practical, evidence-based frontier and homestead techniques, and want more work grounded in archives, measurements, and real performance, consider supporting the channel.